Hi, everyone. Welcome to another Common Lisp study group. I'm your host, Ron Batum with Atlanta Functional Programming. Uh, Today, we're going to be covering the Colton library. A library that introduces well, a statically typed functional. It's described according to its documentation and the blog that was written by Robert Smith. Um, Style warning for those of you who follow him on Twitter. Uh, it's described as a statically typed functional programming language built with Common Lisp, and it's integrated with Common Lisp. It's actually built on top of Common Lisp, so you could think of it like a library. But it's also a statically typed functional programming language in that it brings to Common Lisp a Haskell style type system that's completely built on top of Common Lisp and can work well with normal Common Lisp, and we'll see that a little bit today. Um, Colton started out as a project that now I couldn't find much about its origins, but my understanding is some of it came out from some of the stuff that was going on with from what I've read in various other sources. So some of this may be true, some of it might be just conjecture from those other sources. But my understanding is it came out of some developments that were happening with some of the quantum computing efforts that were happening with over at forgetting think the company name, but the author there while working with Common Lisp encountered that obviously with larger scale systems development it might be useful to have somewhat of a type system built on top of um, a Common Lisp that's a bit more stricter than what's already available. Now, most of you know that Common Lisp, although it is strongly typed, it is dynamically typed in that, a variable that is written in a particular let form can be assigned any sort of value within the course of the scope of the actual um, s- function itself, whether it be a global variable or a lexical variable that's written with let or let star or what have you. Um, Today, we're going to be covering some of the syntax and that's part of the Whirlwind tour that's available in the Colton documentation, which I encourage you all to go look at. GitHub links are on the YouTube description for those of you who are um, uh, going to look ahead. I'm going to be covering some of the examples that are already available in there, just to give you guys kind of a look at field of what's going on, just by running some stuff in my REPL. But in addition to that, we will cover the uh, some of the different pedagogical programs that are available in the project in the source directory, as well as some of the projects that they've already built with it that's also available in the examples directory that's available in Colton. I thought it would be nice to kind of do a little bit of a code review to understand what's going on. My experience with this library is still very brief. I've only looked into it more detailed in the Whirlwind Tour the last couple of days, mainly because I've been dealing with some technical issues related to my Emacs setup for tonight. But it looks like we're good to go, and I can actually get started on this. Couple of announcements before we begin on a more of a detailed discussion of Colton. For those of you who have been following us and been using our meetup, many of you may have actually bookmarked our original Hangouts link. We are now going to be retiring that. I'm going to be posting inside the meetup page for folks who are part of our meetup group. The new meetup link for those so that you can actually join and be part of the discussions. In addition to that, we are going to be also um, leveraging uh, the Jitsi platform for our future meetups. Again, the meetup links are going to be updated inside the meetup announcements for both the Common Lisp Study Group, which is run every Wednesday now from 7:30 to 9:30 p.m. Eastern Time, as well as the Haskell Study Group, which is tomorrow, Thursdays, from 7:30 to 9:30 p.m. Eastern Time. Additionally, as many of you know, Atlanta Functional Programming's mission is to promote the use of functional programming as a dominant paradigm for large-scale software development. And we are looking for speakers like you to come and give a talk on anything related to functional programming that you may be doing on your day-to-day or something that you're doing on the side. And we are a language agnostic group. We are actually trying to kind of document and record, talks on how some people have designed certain of their architectures in a functional manner. For those of you who are interested in actually giving us a talk, feel free to contact me. I'm available as Bugram on the functional programming Slack server. And I occasionally do squat on the Lisp Discord server for those of you who want to contact me via the Lisp Discord server with your thoughts, ideas, questions, maybe even talks that you may want to give as part of our virtual group. We have not yet found a physical venue yet due to pandemic restrictions being up and down right now. Stay tuned to the meetup announcements when we do have that kind of sorted out. Okay, let's begin. As I mentioned, Colton is a brand new library that introduces kind of a statically typed functional programming, has a language, has a library on top of Common Lisp. Why am I calling this, and why does the documentation call this a statically typed functional programming language built on top of Common Lisp? Well, for one thing, it is built on top of Common Lisp, which is obvious, but there's something a little bit more subtler than that. What that means is the packages that Colton defines and its type system as it's defined, as well as any declarations that it's defined, is written in a package that does not import any of the Common Lisp symbols. Now, most of you who know Common Lisp coming in, this means that the package itself does not use the Common Lisp package. All right, the CL package that most of us are familiar with, which defines the majority of the symbols that are used for day-to-day work. This means that when you are interacting with Colton, and we will be seeing this today when we're looking at some of the example programs, you will not be able to use any Common Lisp symbol unless you preface it with prefix it with a CL colon to get the external symbol that's exported from the Common Lisp package inside your thing. Additionally, for the rest of this thing, I must give a fair warning about this because the documentation is very explicit about this. Colton is still in the experimental stages in that meaning that it hasn't actually reached the 1.0 version yet, and we will be at uh, kind of seeing potential changes that is in its syntax. But more importantly, it also means that there are bugs in the implementation that haven't been stabilized. And we may encounter those if you are experimenting with this library and you want to write some programs with it and you encounter some of these bugs, please, please, please put up GitHub issues so this project, can succeed and get to 1.0 so that we can all have this additional library to use for our day-to-day development as part of building stuff with Common Lisp. One more thing to kind of bring to date on this, just because I experienced this and this is part of the installation process. Um, Colton only seems to be working right now, and I've confirmed this, unfortunately, with various different Lisps on the 2.1x branch as is specified in the top level README. Um, The reasons for this is it looks like there's some stuff that they're using that may be non-standard. Common Lisp that might be specific to the 2.1 version of SBCL. So, well, for the time being, while you are developing your Lisp programs, if you are experimenting with Colton, I encourage you to get the latest version of SBCL, which as of this recording is SBCL 2.111, and just try out the Colton library, see what's available, what's limiting, what's not limiting, and you can go on from there. Okay, so the first things first on the Lisp tour of this library from my experiences on this. One is that installation is pretty quick. You can actually just simply clone this guy into your local projects inside your Quick Lisp installation, and this run QL Quick Load Colton, and it should work without any problems. Um, One thing to note is while you are experimenting with Colton, you can also provide Colton inside your own projects using, hashtag Colton in the ASD for the system definition that you're going to leverage a library with. But again, because it is not available on the Quick Lisp, um, it's not available on Quick Lisp in general in the servers to download. Be warned that if you're going to distribute your project, that you may want to put into your documentation at least until it gets available and becomes 1.0, that folks needs to download and install Quick Lisp for their prior to actually downloading your project and compiling it. Additionally, one thing that you may want to do which becomes pretty useful is, and we're going to test this because I just installed this like earlier. You could run actually as the test system Colton, and it will actually go and attempt to run its test suite. Now it looks like its test week is requiring Fiasco, and it didn't actually install that when I installed Colton. So let's see if Fiasco is available on Quick Lisp. It is. So let's go ahead and run this guy just quickly. This is another testing library. I don't know how this testing library compares to the other ones, so it might be required to explore this in another episode of our study group when we go and check it out. I'm going to go ahead and load JSON streams as well. But let's actually do this, Colton/tests, because this will allow it to get everything that it needs. Okay. The reasons why I'm actually testing this out is there might be the new versions of Colton might require us some experiments. I tried this on Mac recently, and it seemed to be working on my Mac, but I just recently got this all set up working on Linux, and I thought I'd show you guys all this on Linux, so that way, for those of you who are working on Linux for your day-to-day, you can actually go ahead and do this. So now let's go ahead and grab it. It looks like all of our stuff is working, so we can actually go ahead and, check out the library. So one prerequisite is defined inside the Whirlwind documentation is the fact that when experimenting with Colton, it might be better to start with Colton user. just because again, Colton itself does not uh, export a lot of symbols inside from the Common Lisp package, and this is going to illustrate that. So let's go ahead and get Colton user and change our REPL to Colton user. Right now, for the time being, I'm going to be showing a lot of my stuff uh, quickly in the REPL, and we can then, transfer some of the stuff over to our buffer as we go along once we get the basics of some of these examples kind of working. Colton actually has an entry point for you to define your code and your declarations and your stuff. In addition, it also has uh, what's it? A way for you to evaluate a given Colton expression, as they call uh, within the context of a larger Lisp system. All right, a larger Lisp function, if you will, right? And the way you do that is you can run the Colton operator, which will actually go in and actually evaluate that expression within the context and environment of the larger Colton top level that's available in your running Lisp image. The reason why these are two different is a lot of the declarations are and top level things usually are required so that the symbols can actually go into some sort of namespace, from my understanding, and it will then do some sort of type checking later on once it actually sets up a lot of the symbol registration, function registration, type signatures, and so forth. And then Colton, the Colton operator, it's going to use that environment to do a lookup and evaluate uh, particular functions and so forth. So let's try some of this out. So the first thing is obviously that we want to check out is how do we define variables and functions within this top level, right? So there we have this function called Colton top level where we can actually go and define this. Here is where we can actually define functions and variables. Now Colton actually ends up taking kind of a a page out of Scheme's book, and it unified actually defining functions and variables under the same define operator. So you can define function variables like so. You can actually use them once they are been defined, like so. You can actually go ahead and define just higher level structures. Like Colton has some tuple definitions already available for us that we can actually go use. This is straight up from the Colton documentation. One thing that is important to note is once this top level has been evaluated, all right, this is now registered inside the Lisp image for type checking later on. Now, let's say that we want to actually go and attempt to use define here with outside of a Colton top level. I think I haven't tried this yet. Like, I don't think this will work. It will actually throw an exception. The reason is again, define is not defined within an external function. It's only available at the Colton top level because the Colton top level parses every other of the expressions that's later on, and it'll actually go in and then load it up. Um, and this is they kind of wrote this condition so to let you know, as you can see, the define operator is only valid in a Colton expression. Let's try a couple of other things too as well. We can actually use Colton to actually define normal strings, booleans, and whatever. They're already been defined. Let's go ahead and define our our standard name. We can define our standard boolean, and we actually do have now a unit much in the same case as if you were using Haskell type units as well, and you get that available here too. Now that we defined a couple of things, obviously we'd like to be able to use uh, these functions. Well, I mean, sorry, these variables. Let's say that we want to actually grab the first variable that's available there. Well, what you could do is you can actually ask Colton to give you that variable once it's been registered inside the Colton top level by simply running the Colton operator that I was mentioning earlier, and then run a Colton expression. Like right now, within Colton, you could provide a form, and it allows you to parse this form within the context of Colton itself. Okay, and this will take in a variable that's available at the in the Colton top level, and it'll then return, you know, the actual value, the underlying Lisp value that that variable returns from the function. Okay, now one thing to note is obviously this will throw an exception if it's not defined. And the way it's defined is going to be has your normal Lisp binding saying that it's an unknown binding. But it actually explicitly tells you that within Colton's environment, this is an unknown binding. It's not saying it's a standard Lisp exception. All right. If you look at the type there in the type thing, is it's saying that the type checker found a type error in the context, okay, within the context of Colton, okay. Colton has its own separate, you could think of its own separate symbol table almost is from what I understood on how some of this stuff is kind of working. Again, there might be some kinks in this, but the basic idea is kind of the same here. Okay. And for those of you watching the live stream, I just want to remind you all, feel free to ask questions at any point in time. I'm more than happy to actually, uh, uh, you know, provide some answers to your questions. Um, those of you who are uh, asking how did I get introduced to this language, obviously this has been on my to-do list. To check out for a while now. It was actually brought up on Cody Reichert's awesome CL list, and it's actually a pretty decent list of cool Lisp libraries to check out. So let's go back here and let's continue on here. So we've defined a few, functions. A few variables, but we haven't actually defined any functions. Um, def- uh, but let's go and first actually do something here. Let's try, see if we can actually do Colton, top level. Okay, and let's do this. Let's see if we could do the same thing here um, in our buffer, shall we? Because obviously we don't want to necessarily just check this guy out. We want to be able to run this differently. Colton, EFP Colton. Okay, so it looks like I did not actually load. Let me restart my Lisp so I can actually get this. Just so folks out there in the web land can actually check out what I'm doing. And let's go ahead and load our Lisp project that I just created here. So I have a quick Lisp project that I created using CL project. I'm going to go ahead and load up Colton overview. So now let's do Colton top level, Colton top level. And unfortunately here, if I'm going to do it this way, I'm going to have to define our stuff like this, because I'm not actually using the Colton user library, but this is fine for now. Y6, let's go ahead and do Colton define T Y. Let's do Colton define P, our tuple. And here is our first thing that I need to show you. Colton's types is part of the Colton library package. If you use Colton user, it actually imports a bunch of stuff. So the two packages you're going to have to define use if you're going to do use package like you see up here is actually going to be Colton and then Colton library. All right. Um, so or you could do what I'm doing right here. For simplicity's sake, let's go ahead and actually do this. Although, again, I'm not a big fan of this. Most of you have heard me rant about this before. I don't like the use package idea just because I'd like to know where my where the exported symbols are coming from. But for simplicity's sake, so that we can actually cover the main features of this library, I'll just quickly, set this all up so that we can actually look at this. All right. Name conflicts with the things. Okay. So let's do this for, right. Let's go ahead and do this and do that. Okay. And right. Give me a second. Comment region. Okay. Let me restart my list one more time. Text. Scale adjust. Okay. Now we'll go load this guy up. Set package. AFB Colton overview. Okay. So now we're going to essentially have the same sort of experience as if we were using Colton user, because this is essentially what Colton user does. But the reason why I didn't normally you don't want to use Colton user because Colton user usually it's bad practice to do, I think, user packages or create defined packages using the library call dash user package. I've never actually seen a project do that. So just kind of following kind of suit here. So let's finish this off here. Let's go ahead and let's add also our string as well as our boolean that we had before, as well as the unit value that we saw. Okay. And obviously I don't like all kind of nice here. And let's compile this. Now everything's compiled and loaded. So now if we go ahead and do Colton FSTP, you'll see if you run it, it compiles and loads. Obviously, it's not going to actually work. But as I said, we can actually go in and sorry, we can actually wrap this Colton expression, this Colton operator, with and call it inside of a Lisp expression. So let's do CL print and then do this, and we can see that we can actually go in and grab the underlying Lisp value and print it out to the standard out. Notice again, like I said, just like if you were using Colton user, because we're not actually importing all the common Lisp symbols, anytime you want to get an exported symbol and directly talk to our Lisp REPL, we're going to have to prefix all of our symbols with the CL colon package, because we're actually trying to grab its exported symbol as part of that package. Okay, so we talked about functions a little bit. We talked about some of the basic types. Let's go and, we talked about variables a little bit, and we talked about some of the basic types that are available to you as part of Colton, but we haven't actually defined any functions yet, right? And obviously, this is kind of useful, we're talking about a functional programming language. We're talking about a statically typed stuff that did for functional programming languages. So how does Colton actually fit into this? Well, we again, as I said, we define our functions in the same way that we defined our variables, in that we create a top level form here. Let me go ahead and say function defining various functions. And in here, we can actually go ahead and define it normally. So again, um, Colton did take a page out of Scheme's book, because most of you who are coming from Scheme and Racket can clearly see that the syntax is exactly the same as Scheme and Racket when you are actually defining a function, right? Syntax is very much the same. Syntax for function definitions, same as Scheme or similar to Scheme. There's a couple things that you'll see Scheme and its derivatives. So there are many other forms, obviously, that you could talk about, but for the time being, we have this, right? Go ahead and indent that because I don't like bad indenting here. Okay. So this is your typical definition. We've seen this before. This is going to be um, a standard function definition. We can actually go ahead and also uh, define functions and we can assign functions to variables, like so. This will also work, and we can actually use the function inside uh, a normal thing here, and you'll see this will also work. Okay. Now, I've not actually talked about type inspection yet. Like if you for folks who are looking at this and are wondering, well, okay, Ram, you're bringing up definitions inside Colton. You're bringing up how but we haven't actually added any types into this. We're gonna get into that just a minute here. But the first things to understand is just how the syntax is very similar, and how it's going to allow you to do what you normally do in Common Lisp straight up in Colton as well, without much of the change other than some small syntactic differences for your function declarations and your variable declarations, right? Um, Instead of actually using your standard CL equivalents, Colton actually also includes a lot of equivalents to many of the functions that are available in Common Lisp, particularly map and its map, reduce, and some of those definitions. Okay, um, an example of this is if we um, end up using map to define just a function that takes in a an anonymous function. Now, anonymous functions, as most of you know in Common Lisp, is the lambda form, right? So it's going to be using the lambda operator in um, Colton. Colton now took a page out of Clojure's book, because anonymous functions are defined with just a standard FN operator syntax, and it's very much the same thing as before. Whereas I think with anonymous functions in Clojure, the slight difference here is it's not using the percent sign to actually define your variables, and so for anonymous variables coming into a function. Folks who are bigger Clojure experts, correct me if I'm wrong. My Clojure knowledge has been somewhat uh, what's the word? It's been deteriorating because I haven't been using it recently. So if there's a mistake in there, by all means, correct me, and I will update and write a comment on this. And obviously, we want to create a list, and there's no way of clearly creating a list, but we have a list constructor, and we can actually provide values into it, and we'll actually go and create a list for us. So this will all work. All right. So now if we go in and say cl print z, sorry, Colton z, and we try running this, you can see that it actually creates a proper list of list form that's a dotted pair of constants that have been mapped to doing x plus 2 here. You can actually also define anonymous functions as well using two variables. So if I believe so, I think so. If we do this, let's say call a function triple, and then uh, if we do this should all work. So now if we want to look at what triple looks like, we could do cl colon print Colton triple, and this should give us the list form function triple. So this is just behind the scenes a standard list function. Okay. All functions in Colton, because Colton is a standard statically typed functional programming language, all right, follows the same approach that every other functional programming language does. A function takes in exactly one input and returns exactly one output. This means multi-argument functions are curried. All right. So an example of this is if we example of multiple functions is if we go in and let's say create a function called and I'm just going to define one, add to, then mm, call it f for lack of a better name for right now, and it takes in 3 arguments. Okay, and what we're doing is we're just going to multiply a times, let's say we double b, and then we square c, right? Although, actually, let's do, yeah, this is fine. Okay, so we now have compile time, play to unified types B to C colon integers. Let me see something here. I may have done something wrong. Let's see here. Compiled form. It's let's simplify this a little bit. Then we'll get to the other problem because that's a type check error. Since we haven't actually provided any information about what A, B, or C are on, we are getting a type check error. So let me simplify this. Let's do C. Okay. Yes. All right. Here underneath, you may not see this, but this here is now a multi-argument function. Okay. We can actually see I mean, a curried function, and we can actually see this if we actually print out. I think if I print out F, you're going to see the top level function input, and we can just go and inspect it. Let's do that. Colton F. Okay. So um, during macro expansion of Colton F, go change this. We name this fx. Fx. Same problem. Okay. All right. It looks like I can't actually see the curried function. That's kind of terrible. I wish I could have. Um, Colton actually hides how it's currying and from a lot from us, but it's important to note that it is a function with multiple arguments and it is curried. So what that means is um, you can actually define later on in your program, later on in a program. So later on in our program, we might end up, maybe doing something like this. Top level, um, define, um, let's just bind one, FMA, FX bind A, okay? And this is just calling FX2. So now we have obviously, if we try to leverage this guy, it's going to it's going to be a two argument function, okay? So this is going to be equivalent to essentially fx bind a is a function that takes in an a and a b. And I'm using uh um type variables in the Haskell sense. So this one, a, b, and c are type variables. For type variables A, B, and C. It may be the case that A, B, and C are all the same, has just the same thing as folks who have been using Haskell. It's the same idea. If we go ahead and use this guy, obviously, let's call our things K or A var, and we just go ahead and, call fx bind A on, 3 and 5. Obviously, if we go ahead and now run what is a var here, you'll see that it's 16 because obviously 3 plus 5 is 8 times 2 is 16. And you can keep on doing this, fx bind a and b, and you can see that this is now going to be, the same thing. It's going to now be a function of single argument here, and it could be a to a here. All right. So this just shows you that you can actually do template specializations and you can actually get um, your standard stuff here. Um, we've actually seen earlier that we can actually create a list, and a list is nothing more than a series of consoles, but this is not a proper list here, as you saw earlier. If we look back at what we had here, make list. Make list took 3 arguments, and let's create another one, a simple one outside of the form. Um, here, here. Hold on 1 second. Okay. Call this define a list, and we can use the make list macros to actually go and create our lists, right? We actually look at this list, Colton, um, a list, you will see, oops, sorry, let me go and unintern this, unintern print. Oh, shoot. Oh, I've interned two things. Unintern, unintern, then unintern print because we don't want them both to be there when I use it. And let's do CL print again. Colton, and our form is going to be a list. So if we do this, you can see that 1, 2, 3, 4 is a proper const list. You may see that reader macro there. The reason why this is displaying this way is because, again, this is a proper list in terms of Common Lisp, but it isn't a proper list in terms of um, I mean, and you can actually display this as a normal Common Lisp list if you end up using the CL package. But right now, the reader macros and read tables inside the REPL are actually following the Colton library, so you won't actually end up seeing those, standard, very nice uh, representations of your Lisp data structures. Okay. I thought I'd mention this ahead of time just because I'm sure that this is a bit jarring for folks who are used to seeing such pretty things like, simple list when we're actually doing this, right? But you'll get used to it once you recognize what it is doing. Okay. One of the nice advantages of this curry syntax that we see here is now that we have a list here, we can actually go ahead and end up using the curried versions of functions inside that are available as part of the Colton library, and they're automatically curried for us. Okay, an example of this is actually the addition operator. Everyone knows that the addition operator takes an A and returns an A. And takes it, well, it's actually two A's and it'll return an A. If you actually go in and run, say, at the Colton at the top level, you could do exactly what we would do in Haskell, and say map uh, +2, okay? Or let's do, we've been doing map double, okay? We're gonna just double everything, and we call this, let's go ahead and call this guy nums. I know I'm putting multiple Colton top levels here. I'm just illustrating these simple forms separate from each other to show you just how quickly it'll actually just look up stuff because these bindings are all in the same top level environment. And if we run this, you could see, did I miss something? Expansions. This can't show up at the top level. What? Failed to parse. Hold on a second. Let me see if +2 works. Open top level +2 times. Da, na, 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 na. Let's see this here. This should actually work. This can't show up at the top level as being a compiler. So this is separate from our things. Let's see here. This takes in a dictionary. We know this works because we've seen this. This is Oh, wait. I think I know what the problem is. This is now. Did I mess up the top level? This is a Colton. So, one. And here. This works just fine. Go ahead and do this in the same function here. Okay, map plus 2. Item plus 2 macro expansion. This cannot show up at the top level. What cannot be shown here? Go ahead and let me wait. We're trying to restart Lisp. Let's go ahead and see if we can debug this here. We know that this works here. Oh, okay. They may have changed something in the default things, but it did not. It's not working here. So the reason why this is complaining, if I define a variable here, I know this will work. Define doubles. Let's say here, and we go ahead and do this. This will work. Okay. It looks like map does not get evaluated at the top level like a REPL. And this might be one of those issues, those stable experimental issues that they want to allow you to do eventually, but they currently don't allow you to do. Like I said, this is a 1.0 library, pre 1.0 library. So some of the features and the user experience is not, completely tied down. So we will encounter some bugs as as I introduce this. But I want to show you kind of the power of this library as we keep going through these examples here. So you can see here now, if we go ahead and CL print doubles, um, sorry, CL print Colton doubles, because again, it's part of the Colton symbol table. If we go ahead and do that, we will see that we've actually doubled everything. We can actually also do the same thing here if we just did that, and you double because we're not adding to, we're actually doubling everything. So that was actually incorrect output. So if we go in and now run this again, you can see that we got the even numbers for 1 through 4. And obviously that's really nice. But what about composition? Because obviously you can't have a functional, but it can't be a functional programming language unless you're able to at least do higher order functions and function composition. At least this is my opinion. I'm not trying to start a flame war here. All right, for folks who are watching this and going, "Oh my God, blasphemy" or something like this, just calm down. Don't worry. I might be saying something completely stupid, and just over the cuff. Just take it. Just let me know this is how you define a functional programming language in your eyes, and let's have a discussion. Let's actually bring that up, as part of our AFP, discussion things. Um, so let's go back to this. So how do we do function composition? Function composition can be done in a couple of ways. Colton provides two different syntaxes for function composition. Okay, if you're trying to do and the reason why there's two different syntaxes is honestly because based on the applicativity of the data to the functions. Okay. Um, a couple things, and actually technically there's two convenient syntaxes for function composition. Let me be more explicit. There's three different approaches to function composition in Colton. Okay, three different approaches. Okay, two of them are macros. Two of the approaches are macros. Okay, and if you're interested, I'll do them. I was planning on doing a macro expansion of them. Okay, are macros. Okay, these are the nest macro and the pipe macro. All right, and one of them is normal composition. Okay, a function called compose. Okay, now what are the advantages of the two functions and the other ones? The two macros. The one thing to note is if you're going to use nest or pipe will compose your functions and then pass your data into do proper applicativity evaluation. And I'll show you again what the different applicativity rules are if you're going to be applying, left to right or right to left, you know, um, uh, uh, or um, and whatnot. But the one thing to note is nest and pipe, because they're macros, they cannot be used in higher order functions inside Colton. Okay. But if you use the compose function to compose your function, or if you even better, also, if you can create a curried function, you can end up using those in higher order functions. But compose, the compose function and curried functions are the only ways to actually allow your functions to be used in higher order functions, at least within the Colton top level. Okay. So what do I mean by first applicativity? Well, let's first talk about function composition. I think most of us know that when we're talking about function composition, if you're given an F and you're given a G, okay, I'm going to use the Haskell syntax of this, and you compose them and you're passing in an X here to F circle G, which in Haskell is F dot G. Sorry. This here is the equivalent of f of g of x. Okay. Now, obviously, this also means that if you do f dot g dot h of x, this is going to be f circle g circle h of x. Okay. It keeps going in that direction. The innermost function is actually applied first, okay, which is the rightmost function. Okay. The applicativity rules go right to left. Okay, the innermost function is applied first to the argument, and its return value is then passed to the outermost until it gets to the leftmost function in this evaluation expression. Okay. In Colton, if you want to follow these rules as is, you can actually use the nest macro. All right. So nest will actually look like the above. Nest expression looks like the above. Right? The pipe expression would require you to actually flip the arguments. Okay. Let's see an example of this. Let's say that we have our standard find square being a function that takes, well, square being um, see if this is, doesn't look like they have power defined. See if I could do that. Well, let's see. let me first check something here before I do this example. Define x squared 4 is being. See what this does. Unknown binding. That's what I thought. Okay. But if I use power, see if that works. Oh, sorry, not power. Why am I thinking this? It N C L E X P T is what it is. Okay, yeah, EXPT. There we go. So this will actually work. Now let's see here. And if we go in and do, let's see, this CL print Colton 4 should give me 4. Let's go into, let's define square as being, I don't know if I could do this, but we'll see. I want to partially apply this to, I think this works, but we'll see. Unknown binding. Yeah, this is still an unknown binding. So obviously there's multiple ways of skinning. I can't do proper partial function application here. I was being too greedy in asking what's available and what's not available. So let's define a function square that takes in an x and then just squares it, okay? So we're gonna just go ahead and take this as the base power and we can actually go in and square it, okay? And now let's also define a function that doubles our function. And we've actually seen this. This actually can be done by doing times 2, okay? Both of these will work. So if you want to actually apply, let's go ahead and create this one more time. A variable x to, okay, just to make things simple. We can actually, if we apply this y, we can actually apply, if we use nest, we could just simply say nest, okay? And we could provide the functions in the order in which we want to apply them. So let's say that we want to first square something and then double it, okay? So the leftmost, if we're using nest, again, it's going to be innermost function is going to be the rightmost argument. So we're going to first have to say double, is we're going to first square it and then double it. And then we can then, provide our actual last argument, which is considered to be a constant function, and it will actually go in and apply this, okay? Now this here is equivalent to double of square of x, okay? Now, obviously we do this, go look into Colton y, and you'll see that we have 8. Why? Because of the fact that it's 2 to the third, essentially, because we did 2 squared times 2, all right? An additional thing that we can do here, though, is, and let's actually make this even better because we want to obviously make things a little cooler for us. It's 18, okay? We want the exact same thing, but if we use the pipe operator, we're going to have to flip it around, okay? What I mean by that is we need to first provide the argument, then we need to provide the rightmost function that we want to use, and we need to provide the leftmost function that we want to use, okay? And this will give us the same result. This is also equivalent to double of square of x. Now, why are there two different syntaxes? Well, for some folks, this syntax is much more familiar or much more amenable to them because they want to see the data flow starting from the source to the sink. All right. Other folks coming from a mathematical world will leverage this section and this syntax because this is more akin to looking at equations inside of like a textbook because mathematics applies the innermost function first and then works out to the leftmost function. Most people are familiar with both of these. Up until recently, function composition was known in this way. Okay, but when I think it was no, not C sharp, it was F sharp, introducing the pizza operator, which allowed you to do leftmost data flow for composition. This started to actually allow more folks to leverage this syntax because you can also apply it differently. Now, there may be other languages. I think Haskell may have something like this where you can apply it the same way. I'm not familiar with it, but I've seen it in F sharp. So folks who are F sharp or Camel fans, if you know of other ones, just let me know. I can, more or less uh, account for those. Report unwanted. Okay. Hide and move. Okay. Okay. Um, let's go on here. Okay. All right. If we look at both of these here, the same result is going to be this. It's going to be the same result. If we print Y, we got 18. If we print Z, we'll get 18. All right. And again, like I said, the data flow will change stuff. But if we go and attempt to use this, as I said before, and let's try creating a variable W that, more or less attempts to use the same sort of double, square, F and N. Well, this will work because of the fact that you're passing it in through an anonymous function. You're wrapping it in an anonymous function. We'll see that 1, 2, 3, 4, this is going to actually work because we've actually passed in an anonymous function. But if you attempt to use this directly, oh, sorry. Attempt to use this directly, though, you're going to end up getting into trouble because this, obviously, for one thing, does not actually create a partial function for you. This is going to actually throw an error saying oh, wait. Wrong thing, sorry. Colon. Oh, sorry. Let's go back. Go back here. Here, you can see here that the nest function, because it doesn't actually return a function, it's going to actually throw up an error saying, oh wait, wrong thing. 1 second. Giving you the wrong error. Here, let's wrap this here and bring that over. Oh, shoot. Um, Meta X SP slurp S expression. Sorry, I don't have currently I don't have a key binding for slurping. I will fix that. So let me go back here, and what I was trying to do is show you what the error was. If we try to do this now, you're going to end up getting what we were expecting. Is it couldn't actually unify the types. The function itself is not a unification, and that's because what nest is returning is not a function. All right. We can actually see this when we try to do cl print Colton nest double square. We'll get the same error if we try doing this here. Okay. Again, that's because it's not actually a a function. It is actually a macro. So the way you would actually end up doing this is if we just call compose double and square, it'll take in two arguments here. Now this will actually do what we're expecting. It'll compile, and if we go look at uh, our W, we'll actually see everyone squared and doubled. And it'll do right to left composition. If I remember correctly, this does not do what pipe does. This is the same ordering as nest, but I may be remembering incorrectly. But let's check that anyway. Yes. The first one is 1 squared is 1 times 2 is 2. Second one is 2 squared is 4 times 2 is 8. Second one is 3 squared is 9 times 2 is 18. Yeah, 16 times 2 is 32. So it is the innermost function. So this is kind of what you would have to do if you want to actually nest some stuff. Notice though, that compose only takes two arguments, an F and a G. So that means if you want to compose more than one, like you would do in Haskell using the dollar sign, or uh, without adding parentheses, you're going to have to actually do some more stuff. I wish they actually adopted the approach that was provided in on Lisp, and figured out a way to actually getting the types aligned. But I'm sure that the problem is getting the types aligned very difficult. It's probably something that is difficult to do, which it's hard enough to do it with two functions. How it might be even more of a nightmare to do it with more. So up until now, we only talked about generic functions. These are actually doing essentially things of f of a arrow a, or for a type variable a. All right. Most of the functions that we've dealt with, even if even if they were multiple arguments, is they were dealing with this. Obviously, we want to actually restrict type variable. Right? We want to actually also to deal with that case. Um, but before we do that and actually start providing an example there on providing your signatures, well, I can actually let me actually try that, and let me actually show you that. So the way you do that is actually pretty simple. Um, you have to actually just simply define um, a declaration. Okay, so let's take an example, another example. Let's do multiply int. Okay, we'll create a function at the top level called define multiply int x y. And we're expecting this to multiply two integers. All right. So this, as it stands, it does not give you obviously a multiplication of two integers. We want to restrict this. So you can actually accidentally provide a string or a character, and it will actually it will throw an error because of the lookup being a problem, but it won't actually tell you why it is a problem, right? So we want to actually go and restrict this so that it gets properly type checked. Okay. Um, the way we do this is we first do, just like any other uh, list function, we define a declaration. Okay. And then we say that this declaration um, is the name of our function. All right. Multiply int. And now we can actually use standard Haskell syntax to actually go and define. And I know I mentioned Haskell quite a bit here, but a lot of the syntax that is driven in this document are very much Haskell-esque. All right. So I'm going to end here, but this is going to be kind of interesting. So here, what we're going to say, it's going to take an integer and another integer and return an integer. All right. We're not talking about numeric types here yet or type classes, although this library does provide type classes and the ability to do parametric types and all sorts of goodies like that, at least from what I read. Um, so this is, but I will. This is going to be this function signature is going to be the last topic I'm going to be covering tonight because there's so many good stuff, and I'd like to give you guys, since my Lisp audience may not have, some of you may not have actually touched type classes. I'd like to first give you guys more of a primer on type classes before we go and talk about Colton's way of doing type classes. Okay, so we're gonna just end on this nice thing here, and then may touch base on parametric algebraic data types, but time permitting. So we have this integer here, and we restricted it here, and we go ahead and we can uh, compile this, and now um, the function is now restricted to only integers. Okay, we could see this when we try to actually leverage um, in a Colton expression, multiply int, and we attempt to do 3.5 times 2. All right, you can see right here, obviously fail to unify types, single float and integer in unification, and it gave you the function signature that it's attempting to do single float integer to A, but you're actually dealing with an integer to integer to integer here. This is what you will be seeing a lot with the Colton type checker. The type checker is actually looking at the function signature, looking at what has been deduced by the inferencer, and seeing if they align. If they don't align, obviously it's going to throw a type error. This is one of the nice things about this. You can actually go ahead and um, do this. Let's say that you wanted only to restrict the first argument as being um, an integer, but the other arguments being any variable. Well, you can actually, I think, use a colon a. um, if I remember the arguments that I've seen earlier. Originally, there were examples that I've seen where the type variable could be any keyword or symbol like colon T. So for folks who are coming from Lisp, may be familiar, this is going to be like the topmost Lisp arguments. This will not necessarily work because we are generalizing um, or attempting to generalize the parametric function to actually take in an integer and do something else with it. So this would be that. Let's see. Compile time here. Da, 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 da. Let me just do something here. Let's see. A arrow, A arrow, A. So what it's complaining about is the fact that I'm creating this using type variables, but I'm not actually adding a type class restriction. Um, but I don't know how to actually address that. I don't without introducing you guys to type classes. So I'm just going to go ahead and, mention that you can, if you want to generalize your stuff, you can certainly do it like this with colon type variables and provide any name for your colon type variables. But normally, if you're going to be coming from Haskell or other languages, usually they start with the beginning of the lowercase alphabet and move in the right direction. So you start with colon A and then work your way forward when you're writing signatures that are going to be um, parametrically inferred, and the types information is going to be inferred. In this case, the reason why this is complaining is because of the fact that we restricted it onto integer, but because A doesn't have any restrictions on it, as in type constraints as to what exactly the type variable that can be passed in, it's resulting into an expression that says, well, the type inferencer will not be able to determine whether or not the operator that you're providing for this function is actually going to match what's being inferred by the type inferencer. All right. So that's just a long-winded way of saying that if I pass in something that doesn't support the times operator, um, and uh, and it's taking in the times operator with an integer, all bets are off. There isn't anything it's going to do. That's why it's kind of failing on this type program in the compile there, because it is a technically it is it's attempting to use Lisp's lookup to actually go and attempt to do the type uh, what's the word, unification, but it's not able to do it. So let's go back and bring this up here. Let's go back to we have this. Okay. The last thing that I was going to cover very quickly is going to be actually um, just that you can define some basic algebraic data types, some basic types first, and then we'll talk about algebraic data types in a second here. But you could define types that are composite types by simply using the define type operator that's available inside the Colton library. So an example of this is, let's create a 3D point as specified in the documentation. It's kind of really nice, and this is going to use a type constructor that takes in 3 integers. Okay. So for folks who are coming in from Haskell land wondering what this looks like, remember there's a data constructor, okay, and a type constructor. All right. So the type constructor is on the left-hand side, the data constructor is on the right-hand side here. So this is the equivalent in Haskell. Okay. This data constructor is what you use to actually go in and, if I'm not mistaken, actually go and instantiate the type, and it will actually go and be used in other places. Additionally, we do have our standard algebraic data types, which are sum types and product types inside Colton. So an example of this is obviously, let's say that we are defining the standard color, which is, obviously either red or blue or green. You can actually specify anything, any other ones that you may want. And this is also going to go ahead and create stuff. You may also want to create tuple structures. So, our product type example is what we just saw earlier. Although it is a structure, it is a product type too, because of the fact that you're treating it as the Cartesian product of the 3 integers that are provided there. If you want to create a generic container or generic type of a particular type, so you may want to create like families of types that match the same structure. Think like generics or templates. Obviously, what you're asking for is a parametric type. You could do it by defining a parametric type, well, a type um, parameterized by a type variable. Now, I've introduced a type variable earlier with the colon A. So we are going to leverage that to actually define a generic tree here. This is an example, another example that leverages the type parameter that we were talking about. Type parameters, you may have noticed, like the colon A, are essentially keyword arguments. That's because of it's being leveraged as a separate namespace to actually keep those type variables separate from the rest of the core library. All right. So generic types are obviously going to end up using those keyword parameters to create your parameterized types. Okay. So in this example, we might be creating a tree. And here, obviously, trees can either be branches or leaves. And in case that if it's a branch, you have, a tree on the left-hand side with the value that the current branch is holding, or a subtree really is what it is, and a tree on the right-hand side. Or you are just a leaf which contains, the value that you provided in there. And this again will get compiled the way you expect it to. And you can actually leverage this way. You can actually create Colton, um, a branch that contains a tree, well, a leaf on this side because it's going to be a red, and then we can have a green, and then obviously we can have another subtree that contains a leaf red on this guy, blue, and then another leaf of red. Sorry, red. And this will all compile and it'll create the tree structure for you. Um, Later on, when we talk about pattern matching as provided by Colton, you will leverage this to write some of the algorithms, and we'll cover some of the examples that I have that we've been covering in Haskell, much in the same way as we continue to explore this library. So next week we're going to continue talking about some of the numeric types that are available, as well as moving on about uh, lists, as well as how do we leverage more stuff about the function signature syntax that I just earlier defined. We're going to expand on that a little bit to introduce things like optional types using annotations, and we'll talk about pattern matching and type classes. Well, time permitting, we'll talk about type classes. So that's it for this week. I appreciate you joining me. Um, I'll see you guys next time. Um, and have a great evening.